Hello everyone, in this video we will cover the section 14.5. In this section we will see the chain rule for functions of more than one variable. So we have several versions for the chain rule, each of them giving a rule for differentiation a composite function. The chain rule is used to find the derivative of composite function. So the first version is that, which is this is the first case of the chain rule. So we suppose that z is equal to f of xy is a differentiable function of x and y. So we consider functions of two variables. X and y are the independent variables. Z is the dependent variable, where the independent variable or independent variables of this function are also functions of t. You see, x is equal to g of t and y is equal to h of t are both differentiable functions of t mainly. Then z is a differentiable function of t, and the derivative of the function z with respect to t, because it is actually a function of t, even if it seems to be a function of two variables depending on x and y, since x and y are also differentiable functions of t. So we consider actually z is a function of one variable, which is t, okay? Because we can write z is equal to f of g of t. In place of x we write g of t, and y is equal to h of t. When we write these values for the independent variables x and y in the definition of the function z is equal to f of xy, we obtain actually a function of t. Just we have one independent variable for this function. Therefore, just we can take actually the derivative of this function with respect to the one variable, which is t. So how can we find its derivative? So for its derivative we use the chain rule, case 1. It is a differentiable function of t, and the derivative of this function with respect to t, since we have one independent variable for this function, we write dz over dt, you see. But f has two independent variables. If we don't consider x and y are not functions of t, then we write del f over del x. First we take the partial derivative of f with respect to x times we apply the chain rule, case 1, namely we take the derivative of the inner function. Namely here, for the first term, we consider the variable y as a constant for finding the derivative of f with respect to x, the partial derivative. And then we take the derivative of x with respect to t, since it is a function of t. Similarly, by considering the variable x as a constant, first we take the partial derivative of f times the derivative of inner function, which is y is equal to h of t dy over dt, or you can write in place of dy over dt h prime t, okay? And another notation for this can be written as, in place of f we can write z, since the dependent variable is given as z. For the function z is equal to f of xy. Therefore, in place of del f over del x we can write del z over del x. Therefore, the chain rule especially is given as dz over dt is equal to del z over del x, which is the partial derivative of the function with respect to x times the derivative of inner function. And similarly, it is valid for the variable y, where z is equal to f of xy, and x is equal to g of t, and y is equal to h of t. Both x and y are functions, differentiable functions of t. For example, if z is given in this form, it is a polynomial where x is equal to sine 2t, it is a function of t. You see, actually we have a function of two variables here. You can consider this polynomial as a function of two variables, f of xy, but the independent variables are also functions. You see, x is equal to sine 2t, it is a trigonometric function, and y is equal to cosine t, which is another one. So let's find the derivative of z with respect to t, because when we write sine 2t and cosine t for x and y, actually we obtain a function of t for the variable z, but without writing them into the definition of the function z, using the chain rule, easily we can find its derivative with respect to t when t is equal to 0. So the chain rule gives, this is the formula, you know, from here. First we take the derivative, partial derivative with respect to x by considering the variable y as a constant. Therefore we have for the first term 2x times y. Actually the constant y is written again, and we take the derivative of x squared, which is equal to 2 times x, and the second one is equal to 3 times y to the power 4 times the derivative of inner function. Inner function is sine 2t. Its derivative is equal to 2 times cosine 2t, you know, plus similarly the partial derivative with respect to y you can find easily, times the derivative of inner function minus sine t. And we can find the values of the variables x and y at t is equal to 0. Writing 0 for t, we get x is equal to 0, sine 0 is equal to 0. Y is, what is cosine 0? Cosine 0 is equal to 1. Writing them here, we have 0 plus 3, you see, 2 times cosine 0, 0 plus 0, since x is equal to 0, minus sine 0. So the second term is 0. The first term is 3 times 2, so we have 6. Okay, it is very easy. Just we use the formula written here. The important thing in here is to take the partial derivatives correctly, and we should remember the derivative formulas. The second version of the chain rule can be given that suppose we suppose that z is again a differentiable function of x and y given in this form generally. So now the independent variables in the preceding case, the independent variables are functions of one variable, but in this case they are differentiable functions of two variables. We have again functions of two variables. You see, x is a function of two variables s and t, and y is a function of two variables s and t. Therefore we have two types for the derivative of the function z. Actually it is a function of two variables. Now it is depending on the variables s and t. Actually here x and y are called the intermediate variables. S and t are the independent variables because s and t are not depending on any variable in this situation, but x and y are depending on the variables s and t, and x and y form another function written here. Therefore they are called intermediate variables, and z is the dependent variable. Of course it is depending on x and y. Also it is depending on the variables s and t. So we find the partial derivatives of the dependent variable z with respect to s and with respect to t, because x and y are also functions of two variables. So the partial derivative of z with respect to s is equal to, first we take the partial derivative of z with respect to x, which is the derivative of the outer function actually, times the derivative of inner function with respect to x with respect to s, which is written as del x over del s, plus similarly for the second variable we do the same operation, the derivative of the outer function by considering the variable x as a constant, times the derivative of inner function, which is y, with respect to s. Similarly, the partial derivative of z with respect to t can be found by using the second case of the chain rule. With respect to x times the derivative of x with respect to t, partial derivative with respect to y times the derivative of y with respect to t. X and y are called intermediate variables, z is the dependent variable, s and t are independent variables. If z is given e to the power x times sine y, you see z is depending on the variables x and y, but x and y are also functions of two variables. X is equal to st square and y is equal to s square times t. So let's find the partial derivatives of the dependent variable z with respect to s and with respect to t. Applying the second case of the chain rule, we take first the partial derivative of the function z with respect to x by considering the variable y as a constant. Therefore, sine y is a constant like the number 2, number 3, and so on. So, you know, the derivative of exponential x is same. Therefore, we write directly itself and we write the constant times the derivative of inner function, the derivative of x with respect to s, with respect to s. Now we consider the variable t as a constant. T square is a number, therefore, like 3s, in place of 3 we have t square actually. What is the derivative of 3 times s? It is equal to 3 with respect to s. Therefore, we write the constant, which is t square for x, and plus the partial derivative of z with respect to y. Now, exponential x is a constant since we consider x is a constant. We write the constant and we take the derivative of the function cosine y times the derivative of the inner function, the derivative of y with respect to s. Therefore, t is a constant here. The derivative of s square is equal to 2s and constant. And the term written here is equivalent to the addition written here after writing the variables x and y in terms of the independent variables s and t. So you see the partial derivative of z is a function of s and t. It is a function of two variables. Similarly, you can find the partial derivative of z with respect to t easily. If you don't understand this computation, please inform me by sending an email to me. So to remember, therefore, we obtain the partial derivatives by using the second case of the chain rule. So to remember the chain rule, it is helpful to draw the tree diagram you see. First, we begin with the dependent variable. So it is depending on z is a function of f of xy, and x is a function of st, and y is a function of st. So first we take the derivative of the outer function, the derivative of f with respect to x and y, or the derivative of z with respect to x and y. As you see the notations for the derivative, partial derivative of the dependent variable z with respect to x and with respect to y. And then we take the derivative of inner functions, which are x and y, because they are differentiable functions of s and t. So we take the partial derivative of x with respect to s and with respect to t, and the partial derivatives of the variable y with respect to s and with respect to t. Another example, so we have a function of three variables. U is given actually f of x, y, z, where the intermediate variables, because they are also functions of three variables, x is given as r times s times e to the power t. So here x is equal to a function of three variables depending on r, s, and t. And y is a function of three variables. Let's write r, s, t, given as r times s squared times e to the power minus t, and similarly the third variable is a function of three variables. Let's say m, r, s, t. So the given function is a function of the variables x, y, and z. We have three independent variables here, but the independent variables of this function are also functions of the functions of three variables depending on r, s, and t. Therefore here x, y, and z are the intermediate variables, u is the dependent variable, r, s, and t are the independent variables, which means u is actually a function of let's say k function of r, s, t. After writing these definitions for x, y, and z in the definition of u. So our aim here is to find the value of the partial derivative of u with respect to s when r is equal to 2, s is equal to 1, and t is equal to 0. So without writing the definitions of the intermediate variables x, y, and z written here into the definition of the function u, using the second case of the chain rule, we can find the partial derivative of u with respect to s. So just we take the partial derivative of the dependent variable u with respect to the intermediate variables written here, del u over del x, del u over del y, and del u over del z, and we write the derivative of the inner functions respectively, and we apply the multiplication here, and we add them, and we obtain the partial derivative of dependent variable. So we have del u over del x times del x over del s, and with respect to y, you see, and with respect to z. That's it. It is very easy. So del u over del x can be found by considering the variables y and z as a constant. Therefore y is a constant here. So the derivative of x to the 4 is equal to 4x3 times, and the derivative of the second term is equal to 0 because it is a constant. We don't have any x here, and y and z are constant for the partial derivative of u with respect to x. And now we take the derivative of inner function x defined here with respect to s, because we want to find the partial derivative of u with respect to s. Its derivative is found by considering the variables r and t as a constant similarly. So r is a constant, e to the power t is a constant, and the derivative of s is equal to 1. Actually, the derivative of this one is equal to r times e to the power t. And similarly, with respect to y, the partial derivative is equal to y is a variable, x to the 4 is a constant, so its derivative is equal to x to the 4 plus y square is a variable, z cube is a constant, therefore we take the derivative of y squared to y times constant z to the power 3 times the derivative of inner function. Similarly, with respect to s, r and t are the constant. The derivative of s squared is equal to 2s times the constant, which is r times e to the power minus t. And similarly, you can obtain the last one by considering the variables x and y as a constant for the partial derivative, and we apply the same way for the inner derivative of inner function with respect to s by considering the variables r and t as a constant. And then writing 2, 1, and 0 for r, s, and t, also we have the variables x, y, and z. We can find them by writing these numbers for the variables r, s, and t in these definitions. Therefore, we write the numbers for the variables written here, and we obtain the value of the partial derivative of the dependent variable at the given point. Another example, let's consider this function gst is given actually the value of another function which is f by writing s square minus t square and t square minus s square for the independent variables of the function f, and we know f is differentiable, which means we can take the derivative, the partial derivative of f with respect to x, with respect to its independent variables. So we show that g, the function g, satisfies this equation. Okay, after finding the partial derivatives of the function g, and when we write the left hand side of this equation, so we obtain 0. So g of st is defined by using another function which is f by writing the functions actually s square minus t square and t square minus s square. They are actually functions of the variables s and t. So to make easier the calculation, let's assign variables for the function f, let's say xy here. So x is corresponding to s square minus t square, you see, and y is corresponding to t square minus s square. So g of st becomes f of xy. And to find the partial derivative of g with respect to s and t, so actually we use the chain rule for the function f of xy, because g is equal to f of xy and x and y are equal to them, written here. So using the chain rule, case 1, it is equal to, namely the partial derivative of g with respect to s is equal to the partial derivative of f with respect to x times the derivative of x with respect to s plus the same idea for y. And then we write del f over del x. We don't know exact definition of f. Therefore, we write again the notation for the partial derivative times the derivative of x with respect to s. We know the exact definition, the explicit definition of x and its derivative with respect to s is equal to s squared becomes 2s minus t squared becomes 0 since t is considering as a constant. And similarly, del f over del y, we don't know explicit definition of f, but we have an explicit definition of the variable y, and its derivative with respect to s is equal to minus 2s. The derivative of t squared is equal to 0. Similarly, you can find the partial derivative of g with respect to t. Therefore, writing this to the term written here, namely t times del g over del s plus s times del g over del t, and after necessary computation we obtain 0. Namely, we will multiply the first one by t, so we have 2st, you see. We have minus here, therefore we write minus here, times t, we have 2st del f over del y, and the second one is multiplied by s, so we have minus 2st plus 2st del f over del y. So by removing them, because we have the same number with exact minus, therefore they become 0. And similarly, we can do the same thing for the first terms in the parentheses. So we obtain 0. So now we see the implicit differentiation. We suppose that an equation of the form f of xy is equal to 0 defines y implicitly as a differentiable function of x, that is y is equal to f of x, where it is defined implicitly by the equation f of xy is equal to 0 for all x in the domain of f. For example, x cubed plus x squared y plus y cubed is equal to 1, where y is equal to some function of x, but we don't know its explicit definition. But this function is defined by writing an equation in the variables x and y. Actually here y is a function of x and x is the independent variable of the variable y. But we don't know its exact definition, but we have an equation between them. We have a relation between the independent variable and the dependent variable of the function. Therefore, we can find properties of this function by using this relation between the independent and dependent variables. So, in this case, we say the function is defined implicitly. Okay. So here, bigger f of xy is defined as writing the number to the left side. So we have actually x cubed plus x squared times y plus y to the power 3 minus 1 is equal to 0. You see, we have a relation between the independent variable x and the dependent variable y, and it is given implicitly. We don't have any explicit definition for the dependent variable y like x cubed plus 1, but we have a relation between them, so it is said to be the function is given implicitly. So if this implicit relation big F is differentiable, we can apply case 1 of the chain rule to differentiate both sides of the equation written here, because it is a function of x and y actually, but y is a function of x. So to differentiate both sides with respect to x, since both x and y are functions of x, so we obtain, namely we use the case 1 of the chain rule, namely del z over del x times del x over del s plus del z over del y times del y over del s actually. This is the formula for the derivative del z over del s. Okay. If x is a function of s and y is a function of s, okay, therefore the variable z is actually given by f of xy is a function of f. Therefore we have case 1 of the chain rule for this example. So instead of z we have bigger F here, so we have already the explicit definition for the first term, which is given x already, and the second one y is given by little f of x. So namely z is given by bigger f of xy. Actually we have bigger f x f of x. So our aim to find del f over del x, or dy over dx, because we know y is a function of x, but it is given implicitly by the equation bigger f of xy is equal to 0. So in this case we want to find a formula for finding the derivative of the variable y with respect to x. So it is equal to, by using the chain rule, the derivative of bigger f over del x times the derivative of inner function, which is the first component. So it is given already, it is a linear function, therefore we write the x over dx. What is the derivative of x with respect to x? It is equal to 1 plus del f over del y, we use the second variable now, times dy over dx. So here we have an equality, namely f of xy is equal to 0. Therefore we have the right side of this equation, the derivative of 0 is equal to 0. So from here, so we will find a formula for dy over dx. Okay, dy over dx. So from here the derivative of x is equal to 1 with respect to x. Therefore we have del bigger f over del x plus del f over del y dy over dx. we write d because y is just a function of one variable. It is depending on x is equal to 0. And from here we can write dy over dx is equal to writing this term to the right hand side. So we have minus del f over del x. So over, we write the coefficient written here in the denominator, del f, bigger f over del y. And shortly we can write minus bigger fx, which is the partial derivative of bigger f with respect to x, over bigger f of y. Actually, you know this formula from calculus 1. This is equal to the derivative of y with respect to x if it is given implicitly by the equation bigger f of xy, namely y is equal to f of x here, and it is defined implicitly by the equation bigger f of xy is equal to 0. So this is the formula for the derivative of this function given implicitly, and this is the proof of this formula. It is obtained by using the chain rule, case 1. Okay, so let's solve an example about that, and you can see the formula here. Find the derivative of y with respect to x, and it is defined implicitly. You see x cubed plus y to the power 3 is equal to 6 times x times y, and we know y is equal to f of x here, but we don't know explicit definition of this function, and we have a relation between the independent and dependent variables, you see. So the given equation can be written as, writing this one to the left side, is equal to 0. So we have bigger f of xy, which is written in this form, and formula gives dy over dx is equal to minus the partial derivative of bigger f over the partial derivative of bigger f with respect to y, and it is equal to minus the derivative of this one with respect to x, which is equal to 3x squared, minus the second one is 0, third one is equal to minus 6y, and similarly you can find the denominator. So we have minus x squared minus 2y over y squared minus 2x. Okay, this is a formula for functions of one variable given implicitly, like this one. So what about functions of two variables given implicitly? So we suppose that z is given implicitly as a function z is equal to f of xy by an equation of the form f xyz is equal to 0. So you see the implicit function is given as bigger f of xy for functions of one variable, but for functions of two variables, so the implicit form is given as bigger f of x, y, and z. X independent variable, y independent variable, and z dependent variable. Here x independent variable, y is dependent variable, you see. So our implicit form for functions of two variables will be like this generally. So this means that actually writing z as f of xy, you see, for all xy in the domain of f, and if bigger f and little f are differentiable, then we can use the chain rule to differentiate the equation, implicit equation, as follows. So first we take the derivative of bigger f with respect to x. Here we have x, y, and f of xy. Here actually we have x and y, but we consider this case like this one. Okay, for example, it can be x cubed plus y cube plus z cube minus xy plus z square minus 1 is equal to 0, for example. X and y are the independent variables. Z is the dependent variable. We know z is a function of x and y, but we don't know its explicit definition. But we have a relation between the independent and dependent variables like this one. So how can we find the derivative of z with respect to x? Because we don't know its explicit definition. But we want to find its partial derivative with respect to x. So what should we do for finding its derivative with respect to x? For this, we will benefit from its implicit definition. Okay, and we will find a formula for this derivative by using its implicit definition. Okay, so from here we write, according to the chain rule, the derivative of f with respect to x times the derivative of inner function. Actually we have xy f of xy. So the derivative of x with respect to x, which is equal to 1, you see, plus the derivative of y, the derivative of bigger f with respect to y, which is the partial derivative, which is the derivative of outer function, and the derivative of y with respect to x, plus the derivative of f with respect to z, third variable, times the derivative of z with respect to x, because we want to find the derivative of z with respect to x, the derivative of z with respect to x, because z is a function of two variables. So we know the derivative of x with respect to x is equal to 1, the derivative of x is equal to 1, and we consider the variable y as a constant for the partial derivative with respect to x. Therefore the second one becomes 0. So here we have just del f over del x plus del f over del z times del z over del x is equal to 0. And if del f over del z, the derivative of bigger f with respect to z, is not equal to 0, so we solve for del z over del x, because our aim is to find this one. So we obtain the first formula. It is written as del z over del x. Writing this one to the right hand side, we have minus del f over del x over del f over del z. And similarly you can find for the partial derivative of z with respect to y, it is equal to minus the partial derivative of implicit function with respect to y over partial derivative of f with respect to z. They are the formulas for the partial derivative of the function z is equal to f of xy, such that it is defined by the implicit relation f xy z is equal to 0, implicit expression for the function. We don't know its explicit definition, but we can find the partial derivatives of this function by using the formulas written here, and this is the proof of this formula, these formulas. For example, let's find the partial derivatives of the function z with respect to x and y using the implicit relation given here. Actually we have a function of two variables x and y. Z is equal to f of xy, but we don't know its explicit definition, but we have a formula, we have a relation written here. So writing the constant to the left side, we have bigger f of x, y and z, like this one. Then from equations written here, we can find easily the partial derivative of z with respect to x is equal to minus bigger f of x over f of z. Namely, we take the partial derivative of f with respect to x by considering the other variables as a constant. So we have 3x squared, the second one is 0, the third one is 0, and the last one is 6 times y times z over, with respect to z, the first one is 0, the second one is 0, third one is 3z squared, and the last one is, this one is equal to 6 times x times y. We take the derivative of this one with respect to z. X and y are constants. The derivative of number is 0, and similarly you can find the other one, and we obtain the derivatives in the variables x, y, and z. Okay, thank you very much.